Okay, good. I'll start. So, good afternoon, everyone. Um, I'll review some of what we did last time, and the first thing I'll do is answer Krishna's question. All trapped surfaces are by definition compact. So, why did we have to explicitly take compact trapped surface in stating? We didn't have to. I should actually remove that. So, just historically speaking, the original definition of trapped surface, I believe, did not say anything about compact. And so, if you see Penrose's work and Hawking and Penrose's work, it uses closed trapped surface. But Witten uses compact in the definition. So, if you have used compact in the definition, you don't have to say it again. Okay, I will restate it in the notes. So compact is in the definition of trapped surface. Now, today, what I want to do is a few different things. We are supposed to prove Penrose's theorem on trapped surfaces, namely the fact that if there is a trapped surface, then space-time is incomplete towards the future. So here's the theorem as I wrote it last time. If M is globally hyperbolic with a non-compact Cauchy hypersurface. Remember, the Cauchy hypersurface you should always think of as a three-dimensional spatial surface. Okay, it's the initial value surface, D minus one dimensional in general. And M also satisfies the null energy condition. Then Penrose's theorem is that if M contains a trapped surface, okay, let's remove this from here, because it is assumed compact, then it is geodesically incomplete. That's the content of the theorem. And as I told you last time, it will come from analyzing the boundary of the causal future, which is a space that I think we've encountered many times, and so we should be quite familiar with it. Before I get to it, however, I want to have a slight digression back to an earlier time when we were talking about prompt geodesics. And while, yes, Sanket, it is necessary, that's Penrose's theorem, right? It is necessary to have trapped surface in order to, no, okay, I see, necessary. No, that's not what the theorem says. The theorem says if there's a trapped surface, then there's geodesic incompleteness. It's in one direction. And I want to explain physically what is the meaning of that theorem by the end of this lecture. So be patient. And in another hour and 15 minutes or so, it'll be clear why we need only this direction. Trapped surface implies geodesically incomplete. Okay. But as I said before all that, I realized that I could have explained prompt geodesics, prompt null geodesics quite a bit better had I given an example. And maybe the example is there in various people's notes. Maybe it's there in Witten, I don't remember. But I like this example because it illustrates the point very beautifully, how a null geodesic can be prompt, how it can also be initially prompt and then later become non-prompt, and how that's related to focusing. So for that, I take my space-time to be a little special, but very simple. It's S1 for space times R for time. So this direction is no longer called X, it's called theta. It's an angle which say goes from 0 to some 2 pi r or something. And this direction is time. So this is called the Minkowski cylinder. And the metric we are going to choose is minus dt squared plus d theta squared. Okay, so we'll give theta some dimension of length, and it'll have a total range up to 2 pi r. It's just got a finite range. Otherwise, it's just 1 plus 1d Minkowski. Now, let's make it a little longer because I'll need that. In fact, as usual, I'm going to run in trouble with my drawing skills, but let's try. Let's try to improve this diagram a bit. Okay. Now, this is a very innocent looking space-time, but it carries a number of subtleties. all of which are related to the compactness of the space. And to see that, let's take a point here, P, and ask what is its future domain of dependence. In fact, its future, causal future. So causal future is obtained by taking these lines at 45 degrees, okay, from P. And now these lines are going to continue. These are null directions from P, and they're going to continue behind the cylinder, and they're going to meet at Q. Okay, I hope this part of the diagram is clear. The null directions going out from P, they are usual light cone directions, but because the cylinder is compact, they actually meet at Q. Okay, and of course, we are free to continue things further beyond Q if we want. Now, Q is clearly in the causal future of P. You can see that the time of Q will be much later than the time of P. It will basically be the time taken for this light traveling along this and going like that to reach Q. So obviously Q is in the causal future of P. Now there's no bending involved because the space-time itself is a circle, but a circle has no curvature. So you have to understand that actually the light ray going from P to Q is straight. It's straight at 45 degrees. One way you can satisfy yourself of that is to cut open the cylinder, then you will have a flat thing and you identify the two boundaries and you get back your cylinder. Okay, so these are all essentially light rays traveling freely. Okay, now let's ask the question. Supposing I take the geodesic from P to like this and like this to Q and continue a bit beyond Q to a point Q prime. Okay, so this is my gamma. And it consists of two segments. It's gamma PQ, PQ, and it has a gamma Q prime. Okay. Now gamma PQ is the part before the focal point. This is the focal point, and gamma Q prime is the part after. Now let's try to see in the clearest way possible why this. So I claim that gamma PQ is prompt. This whole thing I'll call gamma PQ prime. So gamma PQ is prompt, but gamma PQ prime is not. Okay. Why? Well, for that, the first question to ask is what is the causal future of P? And we see that in this diagram, it's a funny space. It's not as obvious as you might think. So obviously, if we go out from P, then what I'm shading yellow is all in its causal future. Okay, but these yellow lines continue behind the cylinder. Okay, that's also shaded. And then it just continues forever along the cylinder till infinity. Everything is in the causal future. This I think you'll all agree. But let's try to understand what bounds this space. Okay, so I'll show you in this highlight, this and this. Okay, it's very difficult to draw because the back of the cylinder is present. Somebody has their mic unmuted, so please mute. I think it's Shubhankar actually. Yeah, okay, done. Okay, so what I want to stress is it's the points above this line and above this line, but now this line goes behind, and behind also we need to be above it. Okay, so did you understand what is the causal future now? It's all the points above this and this. Okay, so in the front, it's the points above this, and in the back, it's the points above that. Okay, now that's easy. What's the boundary of the causal future? So yellow is, this is all J plus of P. What's its boundary? It's a very funny boundary. The boundary of J plus of P is only this and this and this and this. These lines, these two lines, this is one line and this is another line. Together, they are the boundary of J plus of P. Do you agree with that? If there are any questions, please ask now.
Could you please explain the J plus P again, like the yellow shaded part?
J plus of P is the causal future of P.
No. So it's not clear from the diagram, like which region you are covering actually.
Yeah, but you should be able to figure out what region it should be, right?
Yes,
What is the space from which signals from P can go? To find that space, we need to draw the null rays out from P and take everything inside them. You agree with that?
Yes.
Okay. Now, I agree that the diagram isn't great because it's a cylinder and there's a back of it. But let's ask the following question. Supposing I look at a point here. This point is below Q and it's on the back of the cylinder. Can I reach it by from P is it in the causal future of P? This point. Yes or no? This point on the back.
No.
No.
We cannot.
And why? Good. You're right. And why? Because it's earlier than Q, right? And Q is the point I reach by these two null lines. So I can't reach here by null or time-like lines. I can reach here only by space-like lines. So at the back of the cylinder, the causal future is above these two dotted lines. In the front of the cylinder, it's above these two lines. Clear now?
We can reach P to Q dash earlier, right?
Now, wait. Don't get to Q dash. I haven't got to Q dash. I'm trying to calculate a particular space called del J plus of P, boundary of J plus of P, and I want everyone to agree what it is. So first, in order to calculate boundary of a space, everyone must first agree what's the space. Okay, and the space is all the region of the cylinder in the front above this pair of lines and all the region at the back above this pair of lines. So first we must agree on that. Let's not jump to the conclusion, please. Any disagreement with that? Any agreement with that?
Yeah, I agree with that.
Okay, good. Thank you. Okay, so therefore, these are the only lines which are in the boundary of the future. That means the entire del J plus is the union of this with that. You agree? So del J plus of P is, I'll give you 4 arrows. This dotted arrow is going to make the diagram very complicated, but let's do it anyway. This one and this one. 4 lines. It's actually 2 lines, but I've drawn it as 4 lines. Is that clear? We agree? I'm erasing them now. I think I should have never drawn them in pen. They'll just make the diagram unviewable. So del J plus this is this line and this line. Good. Okay. Now let's look at Q prime. Okay. Can we get to Q prime earlier than gamma P Q prime as drawn? Gamma P Q prime is this guy. And I think somebody pointed out that we can. And the way we can is that we can be time-like and we can just wind around here. And this is clearly, we can reach here if we want, right? By doing this. All we have to do is go like this to curve round and we can reach under Q prime. And if we are reaching under Q prime, then we have reached before Q, before the previous curve reached there. We are under Q prime means it's the same space point and we have reached earlier. Okay, let's draw that guy. So a curve like, I hate it when this straightens my lines. A curve like reaches X Q prime earlier. Okay, so by definition, we see that gamma PQ prime is not prompt. Okay. Not prompt. Okay, now let's ask the question. If I had a point, if my point Q prime was not there, but it was here, could I have reached it earlier? By any means. Before I reached Q. Supposing this was my Q prime, is there an alternate curve that gets there earlier? Yes or no? And this time the answer is no.
No.
I could probably draw that point here and call it Q double prime. Okay. Can we get to Q double prime earlier than gamma P Q double prime? No. So gamma P Q is prompt because Q double prime is any point before Q. So basically what we learn is that this geodesic is prompt, is prompt up to Q. And the moment we cross Q, it stopped being prompt. So we've exemplified a property of prompt geodesics. They can be prompt in the earlier segment and they can stop being prompt later on. Okay, is that clear? Now let's notice something. Does Q double prime lie in this space, boundary of J plus? Does this lie in this space? Yes or no? Hello? So my question is both about this point and about this point. Q double prime and Q prime. Does any of them lie in del J plus and does any of them not lie in del J plus?
Q double prime lies.
And good. And Q prime?
No.
Very good. Now you see the connection. Q double prime does lie in del J plus and the geodesic to it is prompt. Q prime does not lie in del J plus and the geodesic to it is not prompt. And actually, any point in the future after this focusing point Q, there's no prompt geodesic going to it. Simply none. It's never prompt. Okay. It's not just that this geodesic is not prompt. There is no prompt geodesic starting at P and going to Q prime. And we can see that because Q prime isn't in del J plus, but we proved that if there's any prompt geodesic, then the destination of that geodesic must lie in del J plus. But del J plus is only this much. And after this time, it has run out. There's no del J plus if we are above that. So there are no prompt geodesics anymore to any point above this time. Okay. And what is the reason for all this? It's topology. This kind of thing cannot happen in ordinary Minkowski space. But the moment I close the circle and make it compact, all these things happen. Last thing to check. What about achronality? We proved a theorem that promptness means achronal. Now, look at this segment. Is there a time-like segment which I can use to join P to Q double prime? There isn't. You can check. Okay, this is a prompt geodesic. It reaches here, but also you can check independently. There's simply no time-like geodesic that goes between here and here. I can draw this, but this doesn't make sense because Q prime is on the other side. If I try to go around the other side and I'm time-like, I'll be too late and I'll have to become space-like in order to reach Q double prime. So there's no time-like line which connects these two. However, there is a time-like line connecting these two, and what is it? Well, it's this thing which comes here and lands before Q prime, and then it can just rest over there as time evolves, and it will reach Q prime. So it's time-like. Okay, so the geodesic gamma PQ prime is not prompt, and it's also not achronal. But gamma PQ is prompt, and it's also achronal. So in one single example, we've illustrated essentially all the theorems we stated about prompt geodesics. The fact that they can turn non-prompt, the fact that promptness and achronality are the same, and the fact that if you have something prompt, its final point where it ends must be in the boundary of J plus. If that point is not in the boundary of J plus, then your geodesic can't be prompt. Okay. And one more thing, which I didn't say, but I'm saying now, which is that for such points over here, which are not in the boundary of J plus, which is very limited in this picture to only this region, for such points over here, up there, there's simply no prompt geodesic from P to them. None. Okay. Now you can begin to understand one reason for that, because look at Q prime. It's actually spatially not that far from P, right? The space direction is this one. So in fact, Q prime, I could, if I take it sort of here, it's very close to P. Okay. And what this null geodesic is doing is basically winding around this cylinder. So in space, it's basically light is propagating forward from me. And after it circles the compact space, it comes back from behind me and then circles again and circles again. And once it starts circling multiple times, it's just not prompt. Okay, so this is an example of non-promptness due to topology. This thing is flat, this metric is completely trivial, but there's still non-promptness. You can also have non-promptness even if topology isn't doing anything unusual, if your metric is non-trivial. Both are possible. And the metric case is the one associated to gravitational lensing. Okay, it's not that the light from distant stars is winding round. It might be, we don't know that it isn't winding round the compact direction, but the gravitational lensing we see is interpreted as bending round a gravitational obstacle, and basically by the galaxies pulling light in and bending it. Yes. If Q prime is not lie in causal future, when did I say that, Sanket? I never said Q prime doesn't lie in the causal future. The causal future is this, J plus, and Q prime very much lies in that. It doesn't lie in the boundary of the causal future. Please be very careful with your terms. It is absolutely in everything in the future here is in the causal future of P. Okay, Q is in the causal future, Q prime is in the causal future, Q double prime is in the causal future. All are in the causal future of P. But Q prime and Q are in the boundary of the causal future, and Q and Q double prime are in the boundary of the causal future, but Q prime is not. Okay, I hope that was clear. Surely, if we interpolate Q prime to an earlier time, it lies on del J plus from a, yeah, that's correct, yes. But Q prime is, when we ask whether something is in the boundary of the causal future, we're asking whether a space-time point is in the boundary of the causal future, not a space point. It doesn't mean anything to ask if a space-time is on a boundary of a causal future. It's a space-time point. So yes, Shikhar, we can always move Q prime earlier and make the space-time point lie on the boundary, namely by bringing it all the way down up to here. But then it's not the space-time point Q prime, it's a different space-time point. We can ask questions about this point. If this was my point, then of course there's a prompt null geodesic, which is this line I'm drawing, and that's the end of the discussion. It's prompt, it's achronal, and everything. But notice where did the promptness fail? It failed at this point. And what is this point? It's a focal point of two geodesics. And everything is happening because the topology is making two different geodesics focus at this point. That's not what was happening in ordinary Minkowski. When the light cone goes out, it just keeps going out forever. But when it's compact, the geodesic that went out here is ending up here, and the geodesic that went out here is also ending up here, and they collide, and that's a focal point. It also shows that you can have a focal point without any non-triviality in the metric, just due to topology. So this example, I think, shows a lot of things. Yeah, do I mean that there is some relation between promptness and compactness of a given topology? Yes. Broadly speaking, compactness makes this. So in this example, certainly compactness makes these geodesics non-prompt if you extend them beyond Q. Okay. Whether it's a completely general theorem, I don't know, but I suspect that whenever you have a compact direction, you always get two ways of going around it. Okay, and those two ways can create focal points, and once you go beyond the focal point, you're not prompt. Yeah, Q prime exists only after some space-time point Q. Exactly. So so this is the boundary. This is the not boundary. This is the, in terms of time, this is the last time that you can find a null, last destination to which you can find a prompt geodesic. After this time, there isn't any prompt geodesic, and there is no point on the boundary of J plus. I wanted to, and I've said it many times, that the weird thing about this example is that the entire boundary of J plus is only this much, while J plus itself goes up to infinity. It just has no boundary. Because if I'm here, J plus is this side, and J plus is also on the other side. So there's just no boundary. J plus is just going all over the cylinder, and it keeps going till infinity. No boundary. Okay. I hope this example has helped you to fix the notions and also fix a little bit how these notions are linked. Achronality, focal points, failure of promptness. These are all linked notions. Good. So this was a digression, and it's taken considerable time, but I really wanted to do this because I think what you take away from this series of lectures is very important. And this is one of them, is that promptness is an important criterion, and that in this example, we were able to very clearly see where it fails, why it fails, how it fails, everything. Okay, now back to Penrose's theorem, and now we have to talk about its proof. So I stated the theorem: a trapped surface implies failure of, so trapped surface S implies failure of geodesic completeness. Okay. So the intuition is the following. There is some fine print in this theorem, and one of the fine print which is very important is assume a non-compact Cauchy surface. Of course, we assume global hyperbolicity, which tells us that there is a Cauchy surface, but we also assume that is non-compact. Now, let's try to understand why, when it's non-compact and when it's compact. So I always called a Cauchy hypersurface sigma. So if I say sigma, it usually means a Cauchy hypersurface. Now let's look at this example. What's a Cauchy hypersurface in this example? It's just a circle. Okay, it's just the initial value surface. It's d-1 dimensional, and it should be achronal. That's basically all. And all geodesics that go back in time from the future must intersect it. And that's obvious, because if I take this circle, it circles the cylinder. Anything coming back in time from above cannot go below without passing through that surface. Okay, so in this example, it's compact. If I was in ordinary Minkowski space, then for it to be a Cauchy hypersurface, it would have to be non-compact. Okay, why? Because if I was in Minkowski, X and T, Supposing I try to cheat and I say my Cauchy hypersurface is only this much from some A to some B, XA to XB. Okay, can it be a Cauchy hypersurface? It's certainly achronal. It's just lying along the x-axis. But of course, I can have null geodesics which come back from the past and fail to pass through it. So it's not a Cauchy surface. Okay, so it's non-compact and compact Cauchy surface tells us something about the space-time. It's not our choice. It's not in our hands to choose a Cauchy surface to be compact or otherwise. In the space-time, Minkowski, every Cauchy surface is non-compact. In the space-time cylinder, every Cauchy surface is compact. Broadly speaking, the compactness of the Cauchy surface will mirror the compactness of the spatial section of the space-time. I hope that point is clear. Okay. Now there's a new question about the old discussion. Why is Q prime not on del J plus P? Is it not on the null geodesic that for? So, okay, you need to think a little more carefully about what is J plus of P. Okay, if this part was on the boundary of J plus P, now we are on the back of the cylinder, then it means that either this side or this side is not in J plus of P. Okay, but I made everyone agree, and I asked you at that time if you all agree, that everything which is above these dotted lines at the back is in J plus of P. Therefore, this segment cannot be a boundary. It lies on a null geodesic, all right, but a null geodesic need not be a boundary, and that's exactly what we are trying to show. This segment of the null geodesic is a boundary, this segment is a boundary, this segment is a boundary, this segment is a boundary, but this segment is not a boundary. Okay, I have a request for you. Please take a piece of paper, fold it, make a cylinder with scotch tape, and draw J plus for a point P. And then tell me what is del J plus. Okay, once you do that, you'll never forget it. And I really mean it. This is how we learn things. Okay, now I'm going to go back to this discussion. So non-compact Cauchy surface is not something I pull out of a hat. It's something that is needed or not needed, depending on the nature of the M, the space-time, the globally hyperbolic space-time that I'm working with. And so Penrose's theorem only applies to those globally hyperbolic spacetimes with a non-compact Cauchy hypersurface. Okay. So that's the first intuition, and let me get rid of that one because that's not the most important. That was an obvious statement I made. Now let's talk of the actual intuition. So let's look at our trapped surface. And this is our trapped surface. It's compact by assumption. And there's a null hypersurface associated to it, which comes like this. Let's take the causal future of the whole thing. Okay, so we have a concept of J plus of S. Remember, when I define J plus of a point, I also define J plus of a set, saying it's just the union of all J pluses of every point. Okay, so I take the light cone beyond every point in S, and I take the union of all those. And so clearly, J plus looks like this. Of course, if I go sufficiently far up and I encounter some geometry or topology, it may change. But broadly, this is what it means. And its boundary is these lines, is this line, if you like, or this line. It's actually one thing. It's all closed like that. Okay. Now, what can we say about this J plus of S? Well, this is, first of all, null. It's a null hypersurface. Okay, maybe I should have said something else first of all. S has dimension d minus 2. J plus is obtained by taking every point of S and going in the future along a null geodesic. So it has dimension d minus 1. And it's a null hypersurface. Okay. Now, the intuition is that if it is achronal, then it's a valid Cauchy hypersurface. Remember, there's nothing like a unique Cauchy hypersurface. Any surface which is achronal and causal, achronal and what is it? Not non-time-like. Achronal and not time-like, space-like or null, is a valid Cauchy hypersurface. And in this case, it's null. And and we can show that it's achronal. Now, how do we show that it's achronal? Well, I've done that in my notes earlier, and it's a theorem which you must have seen. We didn't find time to discuss it, but it's very easy to prove. And the proof is basically coming from prompt null geodesics. Okay. So, I don't want to go through that proof again, but it's very easy to prove, and I'll ask you to check that. So, proved in notes, proved in my notes. And this makes J plus a valid Cauchy hypersurface. Okay. Now, an earlier theorem was that any two Cauchy hypersurfaces can be deformed into each other. I don't know if you remember that. That was a consequence of this foliation, the fact that the Cauchy hypersurface gives off, it gives me, all geodesics pass through it. So all future directed geodesics kind of make some kind of integral curves which will connect any one Cauchy surface to any other. So any two can be deformed into each other. Okay. Now the last remaining step is the but. We have assumed that M has a non-compact Cauchy hypersurface. Now, if we can prove that all along I've been wanting to say del J plus. I don't know why somebody didn't correct me. All these statements were about the boundary of J plus, right? It's the boundary of J plus that's null and achronal. J plus itself is not achronal. J plus is everything in the middle. I don't see anybody correcting me. Okay, I wish you had, but anyway, everything I've been saying is about del J plus, which has dimension d minus 1. Now, if we can prove that del J plus is compact, then we have a contradiction. What's the contradiction? Del J plus has all the properties to be deformed into my Cauchy hypersurface, but my given Cauchy hypersurface is non-compact, while del J plus is compact, and you cannot have a topological deformation that takes a compact space into a non-compact space. You even can't have a deformation that takes a compact space and makes it, maps it homeomorphically to a subset of a non-compact space, okay, to an open set. So this is the contradiction that Penrose wants to prove. Now, let's be clear up to now, what have we proved and what is remaining to prove? So the fact that M has a non-compact Cauchy hypersurface, that's assumption. The fact that del J plus has dimension d minus 1 is obvious, because this has dimension d minus 2 S, and its future is everything, but the boundary is generated only by null geodesics out from S. So this boundary has one extra dimension relative to S, and so its dimension d minus 1, proved. The fact that it's a null hypersurface, we proved. Okay, we even wrote a coordinate system in which you can see that explicitly, that coordinate system involving v and u or v, and then r and theta phi, in which you can see that it's null. But you can also see it from the fact that it's generated by this null geodesics. So it's a null hypersurface. Okay. The next thing, this I didn't prove in the lectures, but I proved it in my notes, is that it's achronal. Okay, and that comes from the fact that if it was not achronal, then prompt null geodesics would not be prompt. Basically, it's a contradiction with promptness. Okay, so therefore, and this also we proved, that any two Cauchy hypersurfaces can be deformed into each other. We explained this quite far back. Okay, we explained this. In fact, we even said that the whole space-time M can be thought of topologically as the product of a Cauchy hypersurface and a time direction topologically. And it's that along that time direction that you can imagine deforming any two into each other. So there's only one thing left to prove Penrose's theorem. It's that del J plus is compact. Okay, and this is really up to here was the conceptual part, that we want to prove that del J plus of S is compact. Actually proving it is a mathematical problem, and I'll just give you a quick sketch. But honestly, if you want to skip the proof, it's fine, but you should have an idea where it comes from. Okay, so the proof comes by a rather clever idea, which is that we take these future directed null geodesics. And so let's consider 2 points, both in del J plus S. One is P and one is Q. Okay. Sorry, I think I went to the wrong page of my notes. Yeah. Okay. In fact, sorry, I think I should take P in to be in S, so not here, but here. Okay. Remember, these diagrams are a bit schematic. Del J plus actually extends all over. So for every point in S, there's a direction going to del J plus, which is null. And there's also a time-like direction going into the future, which generates all of J plus. It's difficult to draw, but anyway, let's for now focus on geodesics from P to Q and beyond. Okay, so this segment, I'll label this as gamma PQ. And if it goes beyond, then I'll just label the whole thing as gamma. So the curve, the null geodesic gamma, has a part gamma PQ. And as usual, gamma PQ is the initial part and it's prompt. And if the future of Q, if we move out here, and if the geodesic goes like that, then gamma is going to be non-prompt. It's going to be starting prompt and becoming non-prompt. Okay. So now we notice that gamma PQ is compact. Why? Because it's a segment, it's this segment, and it contains the endpoint P as well as the endpoint Q. If you go back in my notes, you'll see that the causal future of a point contains that point in the definition. And so this thing has only basically 2 endpoints. It's a line topologically. A line can only have 2 endpoints. If it includes those endpoints, then it's compact. So gamma PQ is compact. And that's true for every prompt geodesic gamma PQ. Okay. Now, supposing I consider gamma intersection del J plus. This is gamma. And this is del J plus. So this intersection is actually the same as gamma PQ intersection del J plus, because beyond Q, this part doesn't lie in J plus anymore. If this point doesn't lie in del J plus, then this whole thing for some segment beyond Q if Q is the last point after which the geodesic leaves del J plus, then gamma intersection del J plus is the same as gamma PQ intersection del J plus. Okay. Now we want to show that this space, gamma intersection del J plus, for every null geodesic going out from S is compact. And the way we are going to show it is that gamma intersection del J plus is contained in gamma PQ because it's the same as gamma. So it's, first of all, let's say it's equal to gamma PQ intersection del J plus, which is contained in gamma PQ. Okay. And this is closed. So it's a closed subset of gamma PQ. Okay. Because del J plus is closed. Now that's another theorem that I already proved some time ago. I should have said that here. We also showed that, yeah, and del J plus is closed, is also proved in the notes. So we are putting lots of different things together. Okay, so this intersection is a closed subset of gamma PQ, and because del J plus is closed. Okay, and gamma PQ we just said is compact. Okay, so gamma intersection del J plus is compact. So this is the first thing we wanted to prove. It's a lemma on the way to the last result. I wrote it here, I think. Yeah, so gamma intersection with del J plus is compact. Okay, now we want, this is one gamma. Okay, moreover, it's one geodesic going in from a particular point in P to a particular point Q in del J plus of S. Okay, now there are many such, because from every point of S, there is a prompt geodesic going into del J plus. Okay, and every one of them has the same property. But now remember another thing, from every point of S, there's not one but two different prompt null geodesics going into del J plus, because there are two null directions orthogonal to S, which we proved last time or time before. Okay, so we basically repeat this statement for all gamma along, all gamma having, let's say, affine parameter U, as well as all gamma prime having affine parameter U prime. Okay. Now, if we repeat this for enough geodesics, that is an infinite set of geodesics along U and along U prime, then every one of those intersecting with del J plus is compact. And this information, together with the dimensionality, okay, shows that del J plus of S is compact. And I hope you can see here that I'm using all the geodesics in this U direction, and I'm also using all the geodesics in the U prime direction. Okay, so all future directed null geodesics intersection with del J plus is compact. That proves that del J plus is compact. If you found this tough going, and I find it tough going, frankly, you can sort of either look it up or you can take it as a theorem, mathematical theorem. Okay, it's something Witten sketches. I think my proof is roughly what Witten has sketched, except that in his notes, I think he didn't mention the second fact, the gamma prime with the U prime. And you see, it is important because if you remember, the trapped surface, the relevance of this to trapped surfaces comes from the fact that they have two outgoing null geodesics, both of which have focal points. And it's exactly at focal points that this phenomenon happens, that the geodesic leaves del J plus and goes out. Okay, so we are using that fact. So we are using all the properties of the trapped surface to say that del J plus S is compact. In fact, if it wasn't a trapped surface, then del J plus S need not be compact. And you can check that for yourself. So in Minkowski, a sphere is not a trapped surface and its del J plus is not compact. Okay, so this is very important. So del J plus is compact, and we have our contradiction because this is compact, but we assume the Cauchy surface is non-compact, but yet del J plus has all the properties, achronality, and the fact that it's a d minus one dimensional hypersurface with no time-like directions in it, space-like or null. Then we have a contradiction because clearly this cannot be deformed into a non-compact Cauchy surface. Okay, the contradiction says that, okay, I should have said this earlier. All this was done assuming that geodesics can be extended beyond their focal point. And this contradiction basically says at least one of the sets, gamma and gamma prime, cannot be extended beyond its focal point. And cannot be extended is exactly the statement of geodesic incompleteness. Okay, so that's the proof of Penrose's theorem. But by now, you might be feeling rather unsatisfied because we haven't discussed any physics that follows from this theorem. And we haven't discussed any intuition. How did Penrose arrive at the idea that let me try to prove del J plus is compact and then show there's a contradiction and therefore geodesics cannot be extended. So this is, if you like, the physics part of the discussion, and it's the part that I want to turn to now. But I would like to pause for questions, and Sambit already has one. How is del J plus closed? Okay, in fact, J plus itself is closed, and so is del J plus. And this is why it's very important to go through my notes. It's theorem 3.2. For any compact subset of a globally hyperbolic manifold, both J plus of K and del J plus of K are closed. It's a little bit tedious to prove, but I've given the links or the references to where you can find a sketch in Witten. And well, involved, it would have been nice if he had given the proof, but unfortunately, he's left the proof as an exercise. And this does mean, I think, that it's not out of reach to go through the details, but Witten has given an intuitive sketch. Okay. Now, if I had to give this series of lectures again, I would have proved these properties, achronality of del J plus as well as closedness of J plus and del J plus much earlier. Okay, I actually brought them in only maybe 2 lectures ago, and that probably wasn't the best planning. But whatever it is, these are provable properties, and they all basically follow the notion of promptness. Okay, so the close association of prompt geodesics with the boundary of the future is all you need to really prove all these theorems. Any more questions? Okay, once you're done with questions, we'll switch gears almost completely to a very physical discussion of Schwarzschild black holes. And now you'll begin to see how the thinking behind this theorem emerged and also what are the consequences of the theorem. So please tell me if you have any questions so far. Okay. So now I'm going to actually tell you something that I hope all of you know because it's part of a first course on gravity, and it's the Schwarzschild solution. Hopefully, I'll be able to illuminate it a little bit and simplify some of the discussions that usually follow it, because we only need a few important physics features of it. Okay. So first of all, I'm not going to derive for you how you get the solution, but the solution is nothing but a metric of the form this, where there's one free parameter and RH, and then there is R squared and the length element of a volume area element of a two sphere. Okay. So RH greater than 0 is a free parameter. And the way to understand the physics of this parameter is to calculate the mass of this solution. Now, there are two things you can do. Either you can calculate the so-called ADM mass, or probably what was done earlier and is simpler, calculate Newtonian approximation to this. So expand this metric and read off from it. I'm not going to do that here. It's in my old different gravity lectures, which are on YouTube and in every reference. Either way, you find that the mass associated to this space-time is actually RH upon 2 g Newton. And so this implies that we should replace RH by the more physical quantity 2 gm. Okay, so far so good. Now remember, this is a vacuum solution, so and it's spherically symmetric. And it's the unique vacuum solution that's spherically symmetric. And it describes the space-time outside any spherically symmetric body. For example, the Earth. This is a valid description of the space-time outside the Earth. The key point here is that there's a mass distribution for the body. So the object which has this mass will have a mass distribution. And if we assume that R, what I've called in my notes, R tilde is the mass radius of the mass distribution, then the vacuum solution is valid only for distances bigger than that. Okay, this is just like a vacuum solution of electromagnetism. If I have a lump of some sphere with some charges inside it, then I solve Maxwell's equations outside. I integrate over a sphere to find the total charge inside. But the statement that the electric field is Q by R squared is only valid outside that sphere of charge. If I actually penetrate the sphere, as you know very well, then the electric field won't be what it is outside. It won't be Q by R squared, it will be something else. Okay, so it's the same. Now, if R tilde, which is a physical parameter of where the mass is concentrated, is greater than RH, then there's no problem, because then the radius at which we are allowed to use this solution, which is greater than R tilde, is greater than RH, and this solution is very well behaved for all R greater than RH. Okay, the problem arises if the reverse is true. If R tilde is less than RH, then there is a problem. Just to give you some physical insight into this, what is actual R tilde of the Earth? It's whatever 4,000 kilometers or whatever is the radius of the Earth. But RH of the Earth, which is easily calculated by taking the mass of the Earth and multiplying by 2g, is about a centimeter. Okay, so we are clearly in this regime for the Earth, and there's clearly no problem. Okay, we are not supposed to use this Schwarzschild solution to describe what's deep inside the Earth. And certainly we are not supposed to go within 1 centimeter of the center of the Earth and say that we insist this solution must be true. It's simply not. Okay, because it doesn't follow from Einstein equations because they're not in the vacuum. There's a stress tensor and then it's a different solution. But if for some reason we could take all the mass of the Earth and cram it into a space smaller than 1 centimeter, okay, that's when this happens. And now there's a problem because we are allowed, so we can have 2 regimes, R greater than RH, and we can also have R less than RH, but still greater than R tilde. And this is what we call outside RH. RH is a quantity of dimensions of length, and this is inside RH. And inside RH is very strange. What happens if R goes below RH? You see that this term changes sign. This term becomes negative. So together with this minus sign, the whole thing becomes positive, and T is now a space parameter. This also changes sign. So R is now a time coordinate. So space and time get interchanged. But the problem is at R equals RH, this metric is singular because this blows up. And also because this goes to 0. If this goes to 0, then our signature basically shrinks down to, so we lose 1 dimension, but also another dimension blows up infinitely, and that looks very bad. So we ask ourselves the question, yes, Scott, you're a little bit ahead of the discussion, but I'm getting there. So to understand this, we ask, what is happening at R equals RH? I'm reviewing stuff that I hope you've all seen before. And the point is, metric is certainly singular in these coordinates. But there are many things we can check which suggest to us that life is not so bad. For example, the determinant of the metric is not singular. And that's because in the determinant, these 2 factors, one going to 0 and one blowing up, just cancel each other's effect out, right? In the determinant, we have to multiply this with this, and this one is the inverse of this, so they cancel. So the determinant is not singular, and we've learned to think of a non-singular determinant as a sign that nothing is really wrong. There's also a calculation one can do. You can calculate the scalar quantity R mu nu rho sigma, R mu nu rho sigma. You could also calculate the Ricci scalar. Unfortunately, that is already 0 because of the Einstein equations. But this is not 0 because of Einstein equations, and it's finite at R equals RH. So this suggests that we might need to suggest that the problem might just be an artifact of coordinates. It doesn't prove that. To prove that, we need to actually find coordinates in which we have the same solution, but no problem. And indeed, we can find the coordinates. And for that, we use a nice redefinition. So first, I define R star equals R plus 2gm log R by 2gm minus 1. And then I define U equals T plus R star, T minus actually. T minus R star, and V equals T plus R star. Now I have lots of coordinates floating around. So you may be thinking, what am I going to do? I've only redefined, I've defined something called R star just as a function of R and some constants. And now I've defined this U and this V. But which ones am I going to pick to be my coordinates? So I'm going to actually pick, and this is not what a lot of people do, but it's actually the simplest thing. Pick R and V as coordinates, not R star. Of course, theta and phi go along for the ride. They're already there. We don't do anything to them. We replace R and T by R and V. So what did I define R star for? Only in order to define V. Okay, and I'm going to keep V as my new coordinate in place of T, but I'm not going to change R. R is still going to be R. And in this form, in this choice, the coordinates become the metric becomes the simplest it can be, and it's extremely illuminating. So now I've started calling RH as 2gm. I get this times dv squared plus twice dv dr plus r squared d omega 2 squared. Now see, the advantage of this is that I don't have to keep telling you that R is a function of R star, which many books will do. In this coordinate system, R is just R. It's the same one that we always had. Only T has been replaced by V. Okay. Now let's examine this metric and ask what happens at R equals 2gm. Well, exactly nothing happens. Nothing happens. The signature of the metric remains Lorentzian for R greater than 2gm and at R equals 2gm and as R becomes less than 2gm, absolutely smoothly. So it maybe nothing happens is too strong a statement. Nothing bad happens. The metric is well defined. Let's try to understand this well-definedness of the metric, just unpacking some details. First of all, if you look at this metric, you see that R is a null coordinate. Always. Because GRR in this metric is 0. Now, this may shock you because R didn't start out being a null coordinate. R was here, and it definitely had a GRR term. So GRR was that stuff, 1 over that. Okay. But after making this change of variables, replacing T by V, but V depends on R star, which in turn depends on R, and treating V as an independent coordinate, it's R which has become null, not V. Okay. What about V? So V is a time-like coordinate for R greater than 2gm. It's a null coordinate for R equals 2gm because then this first term drops out. And dv/dr, the fact that the metric has only dv/dr and not dv squared and not dr squared is exactly the statement that V and R are two null coordinates. And that's absolutely standard because from them I can go back to one time and one space. So two null coordinates is always equivalent to one time and one space. Okay. And V becomes space-like from here if R crosses 2gm. If R becomes less than 2gm, then this minus sign goes away and V becomes space-like. So the nature of V is changing. But nothing singular is happening to the metric. So this is the important feature of these coordinates. They're called Eddington-Finkelstein coordinates. And you may have seen commonly in textbooks that we either use R star as a coordinate or we use U and V as two coordinates. But I find all of those, they have their uses for certain problems, but they're not the ones that make it easiest to understand what the metric is of the Schwarzschild black hole as we go through the singularity. This is the one that makes it easy. Now, I didn't say it's a black hole yet, but let's now look at it. Okay. Now, are there any questions up to this point? I hope I'm correct that this is stuff that people hear have seen before, and I'm just reviewing stuff that you know. Okay. Now, let's try to look at the geometry of this black hole, considering, okay. So this is a, if you like, this is just the R equals constant, okay? And this is R equals 2gm. So if I'm here, I'm at R greater than 2gm. If I'm here, then I'm at R equals 2gm. And if I'm here, then I'm at R less than 2gm. Now let's look at the geometry outside. So outside, we have a null direction, dr. Okay, I can think of it as a vector in this. So now my coordinates are v, r, theta, phi. Okay, so 0, 1, 0, 0 is a null direction because there's no grr term. So if I take 0, 1, 0, 0, this is a null vector. What's the other null vector? There's another one, and it's an exercise which I've given in my notes to show that that other one is 1, minus 1, 0, 0, but with some factors. So actually, I should not write 1 and minus 1. You can see it from this. If I take the metric in this form here, and write the condition that a vector is null, I'm basically writing g mu nu x nu equals 0, where x mu are the components of the vector. And you see that outside, because this is negative and this is positive, so I get a vector which is I believe one. Let me just check this. Yeah. I'm having a small sign problem here. Okay, maybe I shouldn't, I will get confused with signs if I continue this calculation. So let's not do this here and let's leave it for your exercise. Let's just draw some vectors. Okay, so the first thing is, since R is by definition a null radial direction, and I'm going to choose that R points inward. So R is a null vector that goes into this solution, but V is a vector, null vector that goes out of it. Okay, how do I see that? It's because V, it's not exactly V. There's a null vector, sorry, which goes out of it, which is an independent one from R. I'm trying to find some good notation for this, which matches what I did earlier. Sorry for this mess up. Okay, so I think I should say it this way. There are two null vectors here. One outgoing from the sphere and one ingoing. Let me first make the statement and then try to justify it. Okay. Now, if I reach here, this is outside. If I reach the boundary on R equals 2gm, what you find is that we always have two null vectors, but one of them has become parallel to this surface. And if we go inside at R less than 2gm, then we have two null vectors, both ingoing. And the way to see that is that V outside is a time-like coordinate. It's not null. Okay. But V becomes null when I reach R equals 2gm. So on R equals 2gm, I have the two null vectors V and R. Okay. And that means that the null vector outside, there was a null vector outside, which was some combination of V and R. But as I approach the horizon, in the space-time sense, it's becoming parallel to the horizon. And as I go inside, it's pointing inwards. Now, this is a bit of a hybrid diagram. It's apparently a space diagram, but you should think of it as a space-time diagram. And in the space-time diagram, it's easy to see. Problem is that to do that, I would have to introduce Penrose diagrams, and I'm not sure everyone is familiar with that. Okay, so right, I think let's leave this as my statement, and I've given you an exercise which actually you can solve and prove this. Outside, there are two null vectors, one outgoing, one ingoing. On R equals 2gm, there's still two null vectors, one parallel to R equals 2gm and other ingoing, and one ingoing. And inside, there are two null vectors, both ingoing. Okay, and this geometry in Schwarzschild is at the heart of this issue about focal points, because we have seen in a previous lecture that when we have one outgoing and one ingoing null vector, then it means that the one set, the ingoing ones, focus in the future, and the outgoing ones focus in the past. And that's good and that's normal. That's what happens in Minkowski. And actually, the further we are from this solution, the more we are just like Minkowski spacetime. So this is not surprising at all. It might be a weird coordinate system we are using, but actually in the limit when R goes to infinity, you can drop this term and go back to normal Minkowski space, and you can derive this fact that there are two null vectors, one outgoing, one ingoing. The point that you can see from the metric is that when we reach 2gm, the one of the null vectors, which was outgoing, becomes no longer outgoing or ingoing, because it actually becomes the vector V. V itself becomes null, this term goes away, and V becomes a null vector. Okay, and when we go inside, V is space-like, and it's easy to see that in R and V coordinates, both the null vectors that you get are pointing inwards. Okay, and so this statement is equivalent to saying that if we take a sphere enclosing the solution, R equals constant sphere, then for R greater than 2gm, it's a normal sphere with the normal property of outward and inward expansion. But for R less than 2gm, it's a trapped surface. It's a sphere, so it's compact. And for R less than 2gm, it's trapped. And this is the R less than 2gm sphere. I can just draw it here. And the statement is that its outgoing null geodesics in both directions are independent, linearly independent, but both are going inwards. Okay, and it's more than that. We can see from this metric that as R goes to 0, the metric is really singular, and there's nothing you can do to fix that. Okay, there's no coordinate transformation that can fix that. And one of the best proofs is that the same quantity R mu null sigma rho squared, it goes like 1 over R to the 6 as R goes to 0. So actually the Riemann curvature diverges. Okay, also so everything goes wrong with the metric in that limit, and there's an actual singularity. Now let's try to compare this situation with what we've been discussing in generality. In this situation, we have a closed trapped surface. It's just any sphere that's inside the horizon of this solution. Okay. Moreover, so we know explicitly that this gives me two null geodesics both going inwards. We also know that there's a singularity at the origin. And we also, therefore, we know that if these are continued, however much you may continue them, whether they focus or don't focus, we don't care, because they are all both pointing to inward, and inward, as the sphere shrinks, means towards the origin. Or inward always means towards the origin. So they always end up at the origin, and the origin is a singularity. So for the Schwarzschild solution, we can say something much stronger than anything we've said till now. There is a singularity. At r equals 0, and any S2 at r less than 2gm reaches it. So any point on S2 reaches it in the causal future. And now you can begin to understand what was the key purpose of Penrose. This was known much before Penrose. This was like Schwarzschild's work, which was only a year after Einstein wrote general relativity. Okay, maybe he didn't do all the analysis, but by the 30s or 20s or 30s, I guess, Oppenheimer, Snyder, others had studied this spherically symmetric solution. The key difference is that Penrose wanted to consider, do not consider symmetric solutions. And now we can see where his insight came from. His insight was that a trapped surface is a feature of the Schwarzschild solution, and it's easy to see. It's just a sphere inside the horizon. Okay. But if we can argue that a trapped surface is there in a more general space-time than the Schwarzschild metric, without assuming any symmetry, then his theorem says that the geodesics are going to be incomplete, at least one of them. Okay, and so this was the key reason why Penrose's work was significant. It was that it reframed the discussion, which was very easy and well known in the Schwarzschild case, to the more general case without any symmetry, by isolating that it's the trapped surface which is significant. Okay. Now, and you should now at this point go and look at the Nobel citation for Penrose. If it was the case, only spherically symmetric gravitational collapse leads to a singularity, we wouldn't expect any black holes in our universe, because there's no reason why any processes which took place during the evolution of the universe would be perfectly spherically symmetric. The tiniest deviation might have destroyed the Schwarzschild solution completely. Penrose's theorem says, yes, maybe it's not the Schwarzschild solution, but if it's anything like it, even if the symmetry is not there, if it's anything like it at some time, namely there's a trapped surface at some time here, then geodesic incompleteness is a given, and we basically end up with a black hole. Okay. Now there's some questions here. One of the null vectors will always point inwards. Yes. The white hole is a physically different object because it reverses what happens in the future and in the past. And I don't want to get into that, at least today. Okay. I'm not trying to derive the null vectors from ingoing and outgoing EF coordinates. I'm only using ingoing EF coordinates, and there are two null vectors. You see, the point is one of them is the coordinate R itself. That's already null. The other one is a linear combination of V and R. Okay, do you get my point? I'm not trying to use both sets of coordinates. These are only ingoing Eddington-Finkelstein. And you see, it's not, the statement is not that there's one null vector in this set of coordinates and one in that set of coordinates. There are always two null vectors. Okay, in any space-time of Lorentzian signature, there are always locally two null vectors. What I'm trying to say is that one of those null vectors, which was pointing outside the sphere into the future, okay, that one is now pointing inside the sphere into the future once the sphere has entered inside the horizon. This is the key. The other one is always pointing inwards anyway. It's still pointing inwards, but one of them has tilted and it's pointing inwards now. And so what has happened is that a sphere, let me draw a yellow sphere outside the horizon, which was a non-trapped surface with two null vectors, one going outwards, one going inwards, has turned into a trapped surface with two null vectors, both going inwards. Okay, here the null vectors were one going out, one going in, towards the future. Now, it's very difficult to talk of null vectors in a diagram which is spatial. Okay, because the null vector is not a concept in space, it's a concept in space-time. So I'm just trying to give you an idea that as time goes to the future, this arrow tells me that I'm going away from the horizon. This arrow says I'm going inward from the horizon. Okay, and if there wasn't a horizon, if it was just some ordinary star or something, then at any point there would always be a way to go away and a way to go into the center. Okay, and we discussed this already when we introduced this fact that there are two null vectors orthogonal to a space-like surface. If there's one, then there's also another one. Okay, the remarkable thing is that what the second null vector does after I go inside a horizon is quite different from what I would expect, and it's completely derivable in Schwarzschild. It's not derivable in general. We don't even know what's a general black hole solution. But we don't need to know that, because we basically want to argue that a closed trapped surface has to form inside as my solution is collapsing, and it will form whether I'm in Schwarzschild or whether I'm in something close to it, because the formation of this surface has to do with the local behavior of two orthogonal null vectors at every point. So I can talk about it locally, and little bit of perturbation cannot change that. But once this forms, then this is doomed. There's no hope for this surface but to collapse. However, I still haven't stated for you the precise statement of Penrose's Nobel Prize winning paper, because there's one missing thing. So let me say what Penrose did. So he gives up Schwarzschild. He doesn't use it anywhere. And as I emphasize, a lot was known about Schwarzschild even before him, even at in the work of Oppenheimer and Snyder, who studied spherically symmetric collapse. But this was the key decision of Penrose to go beyond it. Now, you might realize that this also was the key decision of Raychaudhuri, which was, again, in Schwarzschild, you can always look at geodesics. All the geodesics are known. You can solve the equations and find them. Also in Friedman, Robertson, Walker in a cosmology. But he wanted to go beyond that and understand geodesics in general. Similarly, Penrose wanted to go beyond that and understand singularities or geodesic incompleteness in general. So you give up Schwarzschild. But he ran up against a very important thing, and that will be the topic of our next lecture on Monday. We cannot give up everything. Otherwise, we don't find any theorem. Okay, there have to be some conditions in which we find a theorem that the space-time is geodesically incomplete. And this leads us to a hypothesis called cosmic censorship. And it's only with this hypothesis that we can prove Penrose's final result. So next time, I'll talk about cosmic censorship. I'll explain why it's needed. It's not needed when we discuss Schwarzschild, because that already has it built in, but we need it to make it clear what family of spacetimes we are allowing. Okay, so they are globally hyperbolic with cosmic censorship. And then we'll be able to prove the main theorem, the main result. Okay, his mathematical theorem we've already proved, but we'll now be able to prove the main result, what it implies for space-time itself. Yeah. Is it good to take two null vectors as two independent basis vectors in spite of V and R? Yes, you can. So you could take the metric in the coordinates u, v, theta, and phi. Okay. It would be somewhat more complicated. And it's the reason, well, I don't know how to say better than this. This is the metric that I find useful. And if you think about it, in a way, this is the metric we've always been working on, because you remember that we had one null direction U, and then we took copies of S along a V direction, which was not null. Okay, even though I called it V over there. So that V can be identified with this V, and the U that we had there can be identified with R. So yeah, it's most convenient, as it turns out, to have one null vector be defined by a coordinate direction and the other to be a combination of coordinate directions, because then that allows you to easily follow what that other vector is doing as you approach the solution and go inside the horizon. How much radiation is emitted by black holes? None. I'm doing classic. This entire set is on classical physics. In classical physics, no radiation is emitted by black holes. In quantum physics, things are different, but many things are different. That requires a lot more discussion. I may introduce some aspects of it on Monday and Friday next week. But so far, we have not done any quantum physics. We're simply looking at causal behavior of classical solutions. Yeah. Any other questions? Trapped surface prevent null geodesics to be pointed outwards. That's why it's necessary to be compact. I think that's a correct statement. Okay. So if it was not compact, that is to say, it was not a closed and bounded surface, then what would happen? Well, obviously, the first thing is that we can't prove the theorem, which I'm going to prove. Maybe wait till Monday. When I prove a theorem on Monday, then we'll bring back the question. You can ask me again, what happens if the surface S was not compact to start with? Yeah. How del J plus is compact? I mean, it extends to infinity and it acts as, no, it doesn't act as a Cauchy surface. Okay, I guess, Sambit, you might have missed an important point here, and maybe I didn't say it. I never said del J extends to infinity. Okay, I basically said del J is whatever is the future boundary of whatever is the future of S, which is something we don't know. Okay, we don't assume it extends to infinity. Rather, what we assume is that a geodesic, after it stops being prompt, for example, like this, can still be continued further. Okay, we assume that the space-time is geodesically complete, and we find a contradiction from which we conclude that it's not geodesically complete. So there's actually a contradiction. If you see Penrose's paper, he states 5 different things. You know, del J plus, I don't remember how he words it, globally hyperbolic, trapped surface, del J plus is, the space is geodesically complete, and so on. The Cauchy surface is non-compact. This says all of them cannot be true. And that's basically what we've also tried to prove here. So I guess the point here, I think this figure makes it clear in what sense del J plus is compact. It is generated by every geodesic going out from here. And this argument that the geodesic has an initial prompt part is the part which is helping us to make the theorem that del J plus is compact. But if you want more details, please look in Witten's article, which has light rays, singularities, and so on, which has a discussion about the proof. I've given it in my notes, the reference, but it's the discussion around page 56, which is section 5.6, Penrose's theorem. Okay, and the important thing here is that we are not necessarily applying it to black holes. We're simply saying trapped surface. Basically, trapped surface implies geodesic incompleteness. Today, I reviewed what we know about Schwarzschild black holes just to give you the idea that what was he thinking about. He was thinking, what is the key feature of the Schwarzschild black hole, which we can abstract to the non-symmetric case. And that key feature is the trapped surface. Okay, and what can you prove by the existence of a trapped surface in a generic situation requires us to bring in cosmic censorship, and that I'll talk about next time. And then we'll see Penrose's final result, which is that once a trapped surface forms, then a formation of a black hole is an inevitable consequence. Okay, so I'll stop here. Yeah, del J plus is compact in the sense that the prompt. See, del J plus is not a space that we know, Sambit. It's not the space it's certainly not the space I've drawn. First of all, I don't know how to say this any better. This drawing looks like a drawing in Minkowski spacetime. And in Minkowski spacetime, del J plus is not compact and there's no trapped surface. Okay. What we basically showed here was that if this is a trapped surface, then del J plus is compact. And then we showed that there's a contradiction with future directed geodesics being complete. Okay, so this is not the picture in general. This is just locally a picture, let's say up to here. We just don't know what happens here. And we are just trying to make theorems based on the fact that del J plus by definition is the causal future of S, and it's the boundary of that. Okay, we've only used the definition. We've not used this picture. We use the picture only locally to make some theorems about the nature of prompt and non-prompt geodesics. That's all we used it for. But I hope you can see the problem with your question. The whole of del J plus is not a sphere cross a null line. That's true in Minkowski spacetime, but that's exactly not true inside a black hole. Okay, remember, ultimately we are imagining this to be inside a black hole, and we are asking what happens in the future of that. And the future of that doesn't look like this, because here somewhere in the black hole we know, or we expect that there'll be a singularity, and that's what we are trying to prove. Okay, so this is not a diagram of Minkowski space, and it can never be, because there are no trapped surfaces. If you like this argument in Minkowski space, you would simply conclude, well, therefore there are no trapped surfaces. You have to give up something. Many different things contradict. You have to give up one of them. Here we assume there's a trapped surface. Okay, we assume the space-time is globally hyperbolic, and we assume the Cauchy surface is non-compact, and then we show a contradiction if the space-time is geodesically complete. Please look at the notes again. Yeah. Okay. Was there some comment, question? We are way over time, so I'm going to stop now. Okay. See you all on Monday. Thank you.